Zizhan Chen received his BE degree in the School of Computer Science and Technology from Xi'an Jiaotong University in China in June 2019. He's currently pursuing a PhD at CUHK, Chinese University of Hong Kong. His main interests include embedded software and systems, mobile systems, and operating systems. And I'll be talking about transparent runtime change handling for Android applications.
Okay, thanks, Trevor. Hello, everyone. This is Zizhan from the Chinese University of Hong Kong. Today, I will present this paper, Transparent Runtime Change Handling for Android Apps. So, Android applications are highly portable, and there are a lot of runtime change handlings. So, when the scenario changes, they will cause configuration changes. For example, when we rotate a screen, attach a keyboard, or switch language, the system configuration change will directly affect the current foreground app. And for example, when we rotate the screen from portrait to landscape, the configuration of the foreground app should be adapted to change the layout from portrait to landscape. And the current Android system adopts a passive restarting-based runtime change handling scheme. And this causes a lot of problems and make it challenging and error-proven for app developers. For example, if the app developer fails to store and restore the data when the runtime change happens, it will cause data loss. So, for example, when we enter the username and the phone number in Twitter and then rotate the screen, then these fields will be lost. What's worse, if the app developers fail to stop the asynchronous task which run in parallel with current activity thread, when the asynchronous return and try to update the views that has already been released, it will cause app crashes. And this is more severe than the previous scenario. And the existing runtime change handling approaches focus on static analysis way, and they try to identify the data to be saved and restored during the runtime changes. However, they have several limitations. Since they cannot predict the app logic, they have a lot of false positive, and they're hard to restore the complex view trees. And also, since they need to directly modify the apps, most of the existing apps need to be redeveloped. So in order to solve this problem, our basic idea is that we don't restart activity, but instead put into a shadow state. So the observation is that we found that the root of the problem is that the activity will be restarted and all the states will be released during the restarting. So our basic idea is that we don't restart activity, but instead put it into a shadow state and create another sunny state activity for the new configuration. By doing so, not only the current states of the old activity can be preserved and migrated to the new sunny activity, but also the future state changes caused by the asynchronous task will also be cached and migrated. So by doing so, we handle the runtime changes at the Android system level, and by doing so, we make it totally transparent to app developers, and none of the existing apps need to be redeveloped. And also, we find that it's more feasible to conduct the runtime changes at the Android system level, since we can directly control the system services. So before we introduce our system, we briefly give an introduction to the background, how Android manages the activities. So for Android, each app, they run in a process, and they have several threads. The activity thread is responsible for managing the UI interface. And the app, they are free to create multiple asynchronous threads, which do some time-consuming works, for example, load a resource or accessing the network. But however, only the activity thread can change the current UI interface because the view tree is controlled by the activity thread. And the activity thread can create multiple activity instances to manage the UI interface. And the Android system, they have a system server to control the life cycle of each app. And specifically, they maintain the app activity stack, and each activity stack maintains several task records. Each task record represents one app, and each task record corresponds to a task stack, and inside the task stack, they have several activity records. And then our RCH Droid, actually we are a cooperation between the ATMS and the activity thread. So the overview is that since we try to handle the runtime changes at the system level, so we always prevent restarting the activity, but instead when the runtime change happens, we directly send the configuration change message to the active thread. And then inside the activity thread, we change it to the shadow state and request to create sunny state activity. And then inside the ATMS, we create a new record based on new configuration and then push it into the stack and send back the token. And then back to the activity thread, we create a new new sunny state based on new configuration and change the current state into the shadow state activity. And to migrate the states, we propose a lazy migration scheme. Specifically, we first build a mapping between the shadow state activity and the sunny state activity. And then when the asynchronous task return, and before it takes effect on the shadow state activity, we will catch this update and migrate the states. And also to minimize the runtime change handling time, we propose a coin flipping based activity stack management scheme. And when we try to find the existing shadow state activity and reorder it to the sunny state activity. And also we propose a threshold based garbage collection scheme to minimize the memory overhead. So we will briefly introduce the detailed designs, and specifically we propose two new states to the Android lifecycle. Shadow state, which is not visible but still live. Then when an activity enters the shadow state, their states are snapshotted and stored, and it can still respond to the asynchronous task. And for the sunny state, activity is shown in the foreground and visible, and they should respond to the change of the shadow state activities view tree. And for the view tree migration, we have two considerations. The first consideration is for the current states, we should snapshot it and restore them. And for the future states, we use the lazy migration. Specifically, we first build a mapping between them. So the mapping is an essence-based mapping based on the observation that when the configuration changes, it only changes the view appearance, but actually they represent the same object. For example, when we rotate screen from portrait to landscape, the button, they look different and displayed on different position, but they are still the same button. So based on this observation, we build a hash table from the view ID to the view object. And then the second step is to migrate. So based on the observation is that although we cannot predict the user behavior without knowing the app logic, however, we find that only the activity thread can update the view tree. So we catch the final event in the activity thread and then do the insert and migration step here based on the hash table. And then also we propose different migration policies for different type of views. And then for the activity stack management, we propose a coin flipping based activity stack management to minimize the time. So we always try to find a shadow state activity that is still alive. And if we can find that, we will switch them to the current top of the stack and change the state. And finally, we also propose a garbage collection based on two considerations. The activity that recently entered the shadow state should not be garbage collected. And the activity that frequently enters and exists, the shadow state should not be garbage collected. So finally, some implementation and evaluation results. So we have introduced minimal modification to the Android system, only 348 lines of code. And we do the experiment on real hardware with 3 app sets. The first app set is 27 apps, which are reported to have runtime change issues. The second is the top 100 apps of the Google Play. And the third is the benchmark apps, which have different size of view trace. For the effectiveness, we can address 25 out of 27 runtime issues. And for the top 100, we can address 59 out of 63 runtime change issues. Some of the issues cannot be addressed because they have some user-defined states which are not stored in the views, and they have not implemented the API. And also, we can avoid the app crash. For example, for the 170 milliseconds, the Android 10, their memory drops dramatically to 0. This is because the touch button calls asynchronous task, and which will try to update an image view, which has already been released. And ASPLOS' successfully handles this issue. And for the performance, we can achieve save about 25 and 38% time with acceptable memory overhead. And finally, compared with the state of art, although the runtime joy can save more handling time, however, they need thousands of lines of code modification to each app, and we don't need any modification to any apps. To summary, we propose ASPLOS' joy to transparently handle the runtime change. When the runtime change, we don't restart activity, but instead put it into a shadow state, and we propose several techniques to minimize the runtime change handling time and memory overhead. So that's all. Thank you.
Great. Let's thank